This is Computer Programming 1 from the University of Washington. I'm Martin Dickey, and I'd like to welcome you back to this course. And may I also say, I hope you're enjoying this course, and I hope you'll still be enjoying it by the time we get to the end of today's lecture, Pointer Parameters. This lecture will be one of the most challenging to deliver of the series. I hope you'll stick with me to the end, because what we're going to talk about today is not only complicated, but ultimately very interesting and useful to programming. We'll be talking more about function parameters. We've discussed them before, but as we'll see very shortly, there are some things we just can't do yet with what we already know about function parameters. We'll review what we know, call by value, and then introduce a mechanism that will give us something new, something we'll call by reference. This new thing will involve a concept called a pointer. We'll discuss pointer types and discuss two new operators in C that are used with pointers. Along the way, and especially toward the end, we'll be looking at quite a handful of examples. Let's start by looking at a rather simple function called move1. We're going to ask ourselves what this function does when it's called by the main showed there. Now, move1, you can see by looking at the code, doesn't seem to do a lot. Has two parameters, x and y. Makes x a little smaller, y a little larger. You might think of x and y as being the coordinates of points in a plane, or perhaps on a graphic screen. If you think of x and y in that respect, then what we're doing, or apparently trying to do in this function, is to just nudge that point a little bit. Subtract 1 from its x-coordinate, add 1 to its y-coordinate, in order to move that point a tiny amount. And that might be something you'd want to do in a graphics program or a game or an animation of some type. So it seems a plausible thing to want to do, and let's see if it works the way we'd like it to. Does it really move that point? To test this out, let's look at the main code. We're calling move1 in this code and passing it two variables, a and b. A has been initialized to 4 and b initialized to 7. So we'll begin by tracing this, and as we do, we'll get a little bit of a surprise. We might think that because we're moving the point, that the coordinates are going to come back changed in a different position. They start out at 4 and 7, and we want them to end up in 3 and 8. But they don't really do that. They end up at 4 and 7, just where they started. In order to understand why this happened, and to help us with the detailed trace we'll do following this, let's remind ourselves about how function calls are executed. The space for local variables and parameters isn't allocated or set aside in memory until the function is actually called. At that point, the parameters get their initial values by copying values from the actual arguments. Only then does the function body begin to execute. Let's trace this through. Two functions are involved, so I've drawn two boxes showing the variables a and b in main and the parameters x and y in the function move1. A and b have the values 4 and 7 from the assignment statements in main. Now we're ready to call move1. X, the parameter, gets its value from the value of the argument a. Y gets its value from b. And so we see the initial values of x and y as the function begins to execute. Now, within the function, the first assignment subtracts 1 from x, giving 3. The second subtraction adds 1 to y, giving 8. We've reached the end of this function. When a function terminates, all of its memory is released, it's deallocated, given back to the system, because variables and parameters are local. They're only used inside the functions. They only exist while the function is executing. So the box I've drawn for move 1 goes away. We can erase it from the screen. And I'm left with the original box for main with A and B completely unchanged. Okay. So this little program is operating exactly according to all the rules that we've learned so far. The only problem is that these rules don't let us do what we really wanted to do, which was to nudge that point a little bit on the screen. We're going to get exactly the same output we started with. The problem is that once we've initialized the function parameters with the values of the call, there isn't any further connection between the call and the function. So if the function does change those parameters, it's only changing that local copy. What we need to get what we want, to actually nudge this point for real, is to somehow have access to the locations of the parameters, not just the initial values that were copied there. To do that, we'll need a new concept in C. We'll need a pointer. In short, a pointer is something that contains a reference to another variable. If you think in terms of the computer being composed of memory that holds the variables, and that variables are just names for locations in memory, you can think of the pointer as containing the memory address of a variable rather than a value. Here are a couple variables somewhere in memory. One of them is named x. Looks like it has an integer in it, a 32. The other variable is named xp. Now it has a very strange content. It has an arrow. That's the way I'm going to represent pointers in this course. Instead of putting numeric values inside the box or a pointer, I'll draw an arrow to the memory location that the pointer references. The terminology we'll use is that x is a pointer to an integer. X is the integer, xp is the pointer to it. So we'll say that the type of xp is pointer to int, and we'll often write it int star, and you'll see why shortly. To declare a pointer, it is a variable, so I need a declaration for it, and I'll need a new piece of syntax. That new piece of syntax is the asterisk. Well, we're already using that symbol in C to mean multiplication, but here's another completely unrelated use for the same punctuation. In the first line, I've declared a variable named x, just as we've been doing since very early in the course. In the second line, I'm also declaring a variable. We should pause and be very clear about the parts of this declaration. The name of the variable we're declaring is xp. The type is int star. So you can see that although there's something new here, the overall pattern of a variable declaration in C has not changed. It was always type followed by identifier, and that's still true. The only difference is that the type is now more complex. The type is not integer, the type is int star, or pointer to integer, and the variable name is x. The picture at the bottom shows these two variables, and somehow or other, and I won't say how now, the content of xp has become a reference to x. Now this had to happen through some activity the program took. It doesn't happen automatically because of the way the variables are named. The name here is totally arbitrary, as it is for all other variables in C. But if somehow xp does contain a pointer to the variable x, then the drawing that I have at the bottom is the right way to depict that. What can we do once I have this relationship? Well, what I can now do is reference x through xp. Let's look at that in the first assignment statement. It says star xp gets 0. Well, in any assignment statement, we always first evaluate the expression on the right-hand side. We do that here. It's very trivial. It's just a 0. So now we know a 0 is going to be stored somewhere. The key question is, where are we going to put that 0? And because we have something new on the left-hand side, we have to pause and think carefully about it. What we have on the left-hand side is this odd-looking expression, star xp. This has the meaning, go to xp and follow the arrow that's inside it to find the place referred to. So we're not going to store that 0 in xp because of the star. We're going to store that 0 in the place pointed to by xp, which is x. So this is pretty interesting. Even though x is not mentioned in that assignment statement, we're changing its value. We put a 0 there. And before that, there was, we don't know what was there. Perhaps garbage. Okay. Next assignment statement. The process is the same, but we're going to go through this business of following the arrow more than once. On the right-hand side is the expression we need to evaluate. That expression, star xp plus 1, begins with one of these newfangled star xp's. This says, go to xp, follow the pointer, and pull out the values stored at that reference. So star xp points to x, and it has the value 0. 0 plus 1 is 1. So the right-hand side of that expression has a value of 1. Now to complete the assignment statement, we're going to store that where? Not in xp, but in what xp refers to, which is x. And so the picture changes in this way. So twice in a row now, I've changed the value of the variable named x, and I've never mentioned x once. Using this new knowledge, we can now go back and write a move1 function that really does change the location of that point. You see it there at the top of the screen, and it's full of these stars. The parameters will now be pointers rather than integers, and so their types are now int stars. I've also changed their names just to emphasize the fact that they're pointers. However, the name you choose for a pointer isn't anything special. It can be any name that follows the rules for C identifiers. Simply as a matter of style and readability, I've used the abbreviation PTR as part of the name. Now when I call this function, I'll have to do something new too. When I call move1, I will have to give the called function a pointer to the arguments rather than the value itself. And the way we do that in C is to put an ampersand operator in front of the variable. So A is the name of a location in memory. It's a variable. Ampersand A is a reference or a pointer to that location. Let's trace this. I think it will help make the matter clear. We have the program on the right-hand side in its new version. I start out in main, assigning values to the two variables. Now I'm ready to call the function, move1. At this point, those local values, those local areas for the parameters are allocated. They get initial values from the arguments. But what are those values? They're not 4 and 7, because I'm not passing A and B to the function. I'm passing ampersand A and ampersand B, the address. And if you remember how we showed addresses when I introduced pointers, we used an arrow. So let's draw an arrow to show this relationship. The parameters now are pointing at the variables in main. Okay. Everything's set up now. We can start to execute the assignment statements in the function. Star x pointer gets star x pointer minus 1. Okay. Looking at the right-hand side of this assignment, star x pointer means go to x pointer, follow the arrow, pick out the value pointed to. That's a 4. Subtract 1 from it. That's a 3. Okay, so we have a 3 on the right-hand side of that assignment. Now, the left-hand side says star x PTR. That tells us where to put this value 3. And where is that? It's not x pointer. We're not changing x pointer. We're changing what it points to. So what changes in the picture? Yeah, the box where that arrow points, which happens to be A. So without ever referring to A, I have just changed the value of A in main. I've changed that local variable. Well, the same thing, or similar thing will happen with the second assignment statement. 7 plus 1 will be stored in the place Y pointer points at, which is B. And I have this picture. Now I'm done with the function. I'm at the trailing curly brace, so that function goes away, and that top box is going to disappear from the screen. It's gone. We're back in main. I'm ready to do the printf. But when I do, those values taken from A and B are not what we started with. They've been changed. That's what we wanted, and that's what we got. And that example is the essence of pointers as parameters. If you can go back now and trace this example, you're in really good shape. Okay. One way to think about pointers is as aliases. You remember the spy James Bond who had the alias 007. Now, if you were the spy chief and you got a message saying, Chief, 007 has just been captured, you would know that James Bond has just been captured, because those are the same people. Anything that happens to 007 happens to James Bond because they are the same thing. 007 is just an alias. And the same is true when you're using pointers. When you look at the value that's being pointed at, you're looking at the real thing. We'll see this in all the examples we look at. Keep it in the back of your mind. Alias is another way of accessing the real thing. Pointers are different from the things they point at because they're references rather than values that we might operate on or want to display. And they're considered different types in C. So int star is called pointer to int. We can also have double star and char stars. Because C cares about types, we have to be careful in our programs to make sure that types match up when they're expected to. In fact, this is a good thing. It will often help us answer questions about what is the right thing to use. Ask the question, are the types the same? Or the question, what are the types? And you'll frequently be able to answer what otherwise might seem tricky questions. We've already seen two new operators. The ampersand is read address of, can be applied to any variable or parameter, and the star means location pointed to. Can only be applied to something that is a pointer. The terminology people use is to dereference or to use indirection. This refers to the process of following a pointer to the memory location it points to. Now, some textbooks, including the one we use in the on-campus version of this course, call these pointer parameters output parameters. And this gives you a picture that something is being changed and given back. That's fine. Not all authors use that terminology, and in any case, don't confuse it with output as we use it with printf. It is a different use of that word. We use pointers in functions like this because there isn't any other good way to get the same result. If I need to change the actual parameter, then I have to use a function. You might object, well, functions can return values, and they can. But a function can only return one value, at most one value, or no values if the function return type is void. The standard return type for a function is only a single type. So if I want to change two things, the function return type is not a sufficient mechanism. I still will need to use pointers. Those are the only uses for them in this course. But if you continue in programming, you'll see many, many other uses. Real C programmers tend to use pointers a lot. There are even standard libraries that you might want to use that expect you and require you to use pointers. In future courses you take, you'll see different kinds of uses for pointers, including the ability to create very sophisticated, interesting, and appropriate data structures. Knowing about pointers also helps us clear up some old mysteries. Early on, we looked at scanf, and I issued dire warnings about not leaving out the ampersand. What was that ampersand? Well, now you know what it was. It's the same ampersand we're talking about with pointers. It's the operator that turns a variable name into a reference to that variable. Now, why does scanf need that? Well, think about scanf. What it's doing is changing something. It's changing the variables after you read data from the keyboard. In the first trial example of a scanf, I have variables with no ampersands on them. Those values are passed to scanf by making copies of them. There's no way that scanf would be able to change them and to store new values in them. That's why we need the ampersands there. Scanf is going to change the values of those variables, and the way we know how to do that now is with pointers. The way to pass the pointer or the address of a variable to a function is by putting an ampersand in front of it. Let's work through another example where pointers are really useful. Here the job is part of a computer graphics system. We have shapes on the screen, including lines, and we may need to find the midpoint of a line in order to perhaps to draw a new line or to do some operation with it. To do this, we'll need a coordinate system that lets us specify points as two numbers, x and y coordinates. If you think back to your linear algebra or to your algebra or high school or calculus, you may remember how to do this. The coordinate of the midpoint for x is the average of x1 and x2, and the same is true for y. When you think about how this would map to a coordinate system, you can see why that's true. So writing the program shouldn't be very hard. It should be just a couple of assignment statements that look somewhat like these. But to make the problem a little more interesting, let's wrap this up in a function. Typically we want to do this when we see a subproblem, especially one we think we'll have to solve more than once in a program or in a project. We want to make a function out of it so we can call it, get it right once, code it once, and then every time we need it, we'll just call it. First step on the way to this function is to do the analysis of the algorithm. We've done that now. We know what the formula is. As we're approaching C code for it, the next step would be to think about what the parameters are. And they also fall out pretty clearly from this picture. It looks like we have a total of 4 input values, that is, values that the function needs to operate. And we're going to produce 2 results. So here we have a little bit of a problem since C functions can only return 1 value. What are we going to do? Well, it seems like a job for pointers. And so mid-x and mid-y will have to be pointer parameters. They're going to be changed, and that's exactly what pointers are for. Let's see what this is going to look like in terms of the function now. Got this big complicated list of parameters. First 4 are all of type double, and the last 2, where we'll focus attention, are parameter types. Pointers to double. Okay. So not double values themselves, but they'll contain pointers to the actual values that will be given to us when the function is called. To trace this, let's take a fragment from main or from some other function calling this, declare some variables there, give some of them values, x end and y end on one end of this line segment have been assigned values. And then call the function. Now we need to have 2 points, and for this example I've chosen to place one of the points at the origin and pass in those values, both zeros, using constants. Okay. Then, to get the values back, I'll need 2 variables, mx and my. Because the function was defined with those as pointers to doubles and not just doubles, I can't pass in mx and my per se. I need the ampersand to say, take the address of that and give it to the function. Let's trace this. Here are the variables in main. I give them values. Now, in the function, when I call it, the first 2 parameters have constant values from the function call. The second 2 parameters get values that are copied from the variables x end and y end. And initially, anyway, mid p and mid y are pointing at areas in main which have no defined value yet. Now, where they're pointing is fixed and isn't going to change. The areas they're pointing to, those variables have not been initialized. We'll now step through the 2 assignment statements in the function. You might want to have a copy of this to leaf back and look at. The first assignment statement assigns a value to star mid xp. That value is the average of the 2 x coordinates, so it's 125. Where does it get stored? Not in mid xp, but in the place pointed to by mid xp. And the same kind of logic will tell us that 50, the average of 0 and 100, is stored not in mid yp, but in the place pointed to by mid yp. So this is what's going to happen by the time the function finishes execution. That's another good example to go back and see if you can work out the trace without peeking at the slides. Let's do a couple more examples. Here's one that might be fun. You know that computers can play games. Computers have got very good at games like chess, checkers, and many other computer games. If we were writing a game program and we're communicating with the humans about where they're moving, where the pieces are on the board, we'd want to refer to those by the row and column where the piece was displayed. But internally, the graphics package is going to use an XY system like the one we just used in the previous example. And there, a point on the screen may have weird floating point number values. And in any case, within a particular board position, a square on the screen, there are many such graphics points or pixels. So the problem, a subproblem on a solve, might be to convert an XY graphics position to a row and column position. For example, if I click with the mouse on the screen, I will get back an XY form of the location. But if I then want to say, you clicked on row 3, column 6, I need a function that can translate from the mouse position, that is the graphics position, into the human or board position. This will take a little analysis. Okay? Remember, there are lots of points, graphics points, within each square. So one way to get started is just to look at the geometry involved and notice what constants exist and think about what kind of formulas might work. First of all, we know that all the squares are of the same size. Or we can make that assumption. We can check to see that is that allowable requirement. So the squares themselves are all of the same size, but they're not all in the same position. Okay. Different squares in different positions. In order to get away from this dependency, we may try to refer to position relative to some fixed point. A typical fixed point in a graphics system is the origin. Now, it may be that the origin of our chessboard or checkerboard, the lower left-hand corner, is not literally in the origin of the graphics system as is defined in the graphics package or on the screen. Because we don't know exactly where that is, it would be wise to refer to that by some symbolic name. So that's what I've done. The arrow that points to the origin, I'm going to say that symbolically the location of that origin is LLX, LLY, standing for lower left X and lower left Y coordinates. Okay. So given that as the origin, how do I move about and get to other squares? Well, each time I move one square to the left, I'm adding an amount equal to the square size to the X parameter. And if I move up one square, I'm adding an amount equal to the square size to the Y coordinate. Okay. To go in the other direction, it seems like what I need to do then is divide. I have an X coordinate. I want to find out how many squares it contains. Now, I don't want that to be relative to the origin of the graphics system, but rather relative to the origin of the board. So before doing this division, I should subtract the origin of the board, LLX, from X, and then divide by the square size. Okay. So having done this analysis, let's see if we can turn it into the right code. My function seems to need 4 parameters, the coordinates on the screen which I'm given, and then the position on the board which I'm trying to compute. Now, the first 2 won't be changed by this function, but the second 2 will. That's what we're trying to find out. So they will need to be pointers. From my analysis of the geometry, I've defined some constants that I can put at the top of the program, LLX and LLY, square size. We can easily change this if during testing we find that location isn't in quite the right place, or if the square size isn't exactly the size that we expected it to be. We'll write our program so it doesn't depend on the exact values of these constants. Now, what are the statements I need to fill in? Well, as my analysis just showed, to find either the X or Y coordinate, I need to take the screen coordinate and subtract from it the coordinate value at the origin for that dimension, and then divide by the square size. This will give me the number of positions I need to count over to get to the right square. You might be concerned that this would give me a fractional answer, like row 2.3, column 6.7. But we can easily truncate the answer just by using integer division. Another case where integer division, throwing away that fractional part, is the right thing to do. Once I've finished the division, I have an answer, and I want to assign it, but not to the local parameter. I want to assign it to the value pointed to by the local parameter. So the right way to say this is star row P gets the value that was just computed. I call this from another function such as main. It would look like this. The first 2 parameters are being passed by value. The second are being passed by reference, and so I have to make sure there's an ampersand there. Otherwise, the types would not match up right. The function is expecting a pointer to an integer, and so what I pass into it has to be a pointer. Let's take another problem. Okay. Another problem where it seems like pointers are the right thing to do. Here the problem is that I have a couple of numbers, and I want to get them in the right order. So if the numbers were given to me as 12, 3, that's the wrong order. I want to reorder them as 3, 12. On the other hand, if the numbers are already in sequence, like -1 followed by 5, then there's no change. So I would want the function to test for that condition and not reorder them if they were already correctly ordered. Now, we're changing either nothing or 2 things in this function. So we're either going to change both parameters or we're going to change none of them. This might seem like a trivial and contrived example, but it's actually the first step on a long road. We'll follow some of this road later in the course, and if you stick with computer science, you'll spend lots more time on it. It's the problem of putting things in order in general. This problem is called sorting, and it's an incredibly important and amazingly well-studied problem with many, many interesting algorithms and techniques. Our version of it here is very simple, but it is a step in that direction. Here's some code, and I claim that this code will work. We have two integer pointer parameters. The heart of the algorithm is making a check to see whether any work needs to be done, and if so, going ahead and doing it, swapping the two values. What does it mean to swap? Well, it means that both values have to be there when we're done, but they have to be, each one has to be in a different place from where it started. You might ask yourself if this algorithm would still be correct if I left out the line that said temp gets star P1. Turns out the answer is no. The operation of swapping or exchanging values in two variables turns out to be a useful one that occurs in lots of problems. So even though the original reorder function was already pretty small, it's quite useful to abstract the swapping part out and make a separate function out of it. Let's do that. So the function swap is just like reorder, except it doesn't make a check to see whether the elements are in order. It will do that anyway. Once we have swap written, we could go back to reorder and program it so it doesn't have the assignment statements in it directly. It makes a call to swap. And this is the approach we always like to take when we have a function. Once we have it written and debugged, we like to call it where it's needed so we don't have to do the debugging again. Here's what reorder would look like. Now, the parameters, of course, don't change. Reorder still has to make the check to see which value is a greater, because we didn't put that into the swap function. And then it's going to call swap. So the question I want to pose to you is, what goes in the blanks? Swap needs two values, or two arguments. What should go in the blanks? What do we pass to it? Well, if you're following somewhat blindly and you realize that swap is going to change what it's given and that the parameters of swap are pointers, this is the solution you might first write down. You might be tempted to say swap has to pass a pointer. The way you get a pointer is to put an ampersand in front of the variable. So the first parameter is P1 and better be asterisk, or excuse me, it better be ampersand P1 to make it into a pointer. Well, that's wrong. That won't work. Why is that? Well, what is P1? What type is it? This question of what type is something you can often use to help answer what otherwise might seem tricky questions. What type is P1? Well, P1 is declared as one of the parameters of reorder, and its type is int star. Okay. What is swap expecting? It's expecting an int star. So P1 is already the right type. P1 is the answer that should go in there. If you say ampersand P1, you've gone too far. You've changed the type. Ampersand P1 would be something like a pointer to an integer, and that's not what swap wants. It wants a pointer to an integer, and that's what we have already. Okay. So the answer has to be P1. Okay. The moral is that just blindly putting ampersands in front of arguments being passed to functions that expect pointers is not correct. You have to stop and think about what the type is. Let's trace this just to make it crystal clear. We have 3 parts of the program. Down in main are the variables x and y, and they're initialized with assignment statements. Then we call the function reorder. Reorder has 2 parameters. They're both pointers to integers. So they can be drawn this way with arrows that point into the variables in main. Reorder takes the if statement, does the comparison not between P1 and P2, but between the values they point at, between the 17 and the 42, and it turns out the condition is true. So reorder will call the function swap. Now swap has actually 3 things to keep track of. It has 2 parameters, which are pointers, and 1 local variable, which initially has an unknown value. Okay. Where does P point? This is quite crucial and really quite interesting. Okay. P in swap gets its value from P1. Now that value is an arrow. So the way to think about this is that to initialize P, we took that arrow and made a copy of it and put it in P. We took the arrow that was in P1 and put a copy of it in P. So both P and P1 point at the same place. If your instinct was to draw an arrow from P pointing at P1, that would be a wrong analysis. Okay? The same thing for Q. Okay. Q and P2 are pointing at the same place. So as I continue the trace, if you look at the assignment statements are there, I'm going to set the temp equal to x, or rather to star P. Okay. And so it gets the value pointed at by P. And then I assign what P points at to something. Okay. What it points at is the variable x in main, although x does not appear as a name in swap itself. And the same sort of thing happens with Q. Now, when swap ends, it goes away. When reorder ends, it goes away. Main is left behind. And those 2 values have been swapped. Again, another trace that might have been a little painful to go through, but it's really quite important that you can understand these small examples. If you can, you'll be in good shape when you go on to a more complicated one. If you can't, then it's really important to understand where you went wrong and to go back and carefully do it again until you can see why it works the way it does. Let's take one more look at scanf. Here's a little problem that might occur if you're programming a user interface. We're going to ask the user a series of questions. Maybe this is a census-taking program or one of those annoying telephone surveys I always seem to call just at dinner time. And all they want is a yes or no answer. You're not allowed to say anything else, or in this case, to type anything else. You can only type character Y or character N. And if the user doesn't, you want the program to keep asking. Tell them they made a mistake and keep asking until they type one of those. And only then give the input back. So as a function, here's how we might do it using a single parameter that's a pointer type. Now, in this case, there's only one value to give back, so an alternate way to design the function would be to have a char return type. Just for practice, let's not do it that way. Let's do it the way that's shown with a single parameter. Okay. And to test how this works, let's call a function from main, and main wants the answer, the y or n, to be placed into the variable ch. Okay. When you fill in the code for this, you'll end up writing a scanf or 2. You'll write a scanf, in fact, every time you have to repeat the question if the user gets it wrong. The scanf is going to read a character, so we know that the control string will have a %c in it. Now, what about the variable itself? I've been trying to drill it into your heads that you always have to have an ampersand. And yet, here's an example where there's no ampersand. So am I changing my mind? Is something new going on here? What's the situation? Am I trying to trick you into saying that there's an error? Well, what's happening here is the same as in the previous example with swap. We're paying more careful attention to types, and because we now understand pointers, we can reason through whether or not an ampersand is required. At the beginning of the course, I had to make a flat rule, always use an ampersand. But that really was overkill. There was a principle involved, and now that we know it, we can decide whether or not an ampersand is needed. Okay? What is CHP? It's not a character. It's a pointer to a character. And it points at the character we want to change, which is down in main. And so the right thing to do is to give scanf CHP, just as it is, so that scanf will store the character where it should be stored, in the place pointed to by CHP. So the moral is not that scanf always needs an ampersand, but that it always needs a pointer to where the data is going to be stored. So if the variable or the parameter you're passing is already a pointer, then you need to stop and think about whether or not the ampersand really is required. Let's wrap up and try to summarize all of this. Pointers are going to be needed in functions when the parameter value may be changed. In the syntax, the ampersand creates the pointer, and the asterisk dereferences or follows the arrow. Okay. Now, with this concept of passing parameters by reference, we finally reached the end of our technical discussion of functions for this course. Okay. It's perhaps unfortunate that in C, this last technical topic was so intricate. But it is important, and you will find it useful once you've mastered it. Even though we know the technical ins and outs of functions now in great detail, learning how to use functions and how to design with them will continue to be a challenge. It continues to be a challenge for programmers throughout their careers. It's the very heart of programming and problem solving using C. So we will still, please join me next time as our course continues.